Okay, so thank you very much for the invitation to speak. This is based on work that's ongoing with my postdoc Wieland Stessens and diploma student Martin Rübker in Mainz, and it's also based on some earlier work with Stefan Förster we did in 2011. So rigid branes, I'm working on torus and toroidal orbifolds. Rigid branes you can obtain if you have specific toroidal orbifolds, namely those which have two generating factors. And the reason is that if you have these two different generators, then in a ZL twisted sector, a ZK twist might generate a phase which is given by the greatest common divisor of these two orbifold groups. So in this talk I will focus just on K and L equals 2 and a multiple of 2. And if you have this, then the greatest common divisor is obviously 2. And then you get that the discrete torsion factor is +1 or -1, where the name is +1 is no torsion and -1 is with discrete torsion. So why is this interesting? First of all, usually we have much too many moduli. And some of the moduli are not really useful for us for model building, whereas others can be useful. So when you switch on the discrete torsion, so the -1 here, basically you exchange the role of scalar and complex structure moduli, and generically you get more complex structure moduli than before. And associated to that you also get more 3 cycles than before, and you can use these 3 cycles for model building with D6 branes. So these D6 branes are stuck then at the singularities of the Z2 singularities, and that means since they are stuck, they have no open string moduli, they cannot move away from the fixed point, and therefore they are rigid. So it's on the one hand less closed string moduli, and on the other hand less open string moduli. So why is it really less closed string moduli? It's really that the complex structures take part in the supersymmetry conditions with the D6 branes, so some of them are fixed if we have the D6 brane present. The bad news is, of course, we don't get rid of all the moduli by construction, but we always have at least 3 of the scalar moduli left over because we cannot fix the 2 torus volumes in these models. And then in general there's also some vectors from the closed string sector which don't have any charged matter with it, so they are candidates for dark photons. So on a technical side, if you have these orbifolds with discrete torsion, you have 3 different Z2 subvectors, and you have, in addition, you have orientifold planes where you have just the orientifold plane, and then you have the combination of the Z2 factors with the orientifold plane. And you have a consistency relation that comes from worldsheet duality, which tells you that the discrete torsion factor has to be equal to the product of sign factors that are related to the orientifold planes. And these sign factors mean if you have a -1, it's an exotic orientifold plane, and if it's a +1, it's an ordinary orientifold plane. So if you switch on discrete torsion, it means we need an odd number of exotic orientifold planes, and the only way to obtain models which have supersymmetric D-branes if it's just one exotic orientifold plane. So to give you some details on how the model building proceeds, let's talk about an example where you get gauge enhancement. So a rigid D-brane, as I said, is stuck at Z2 fixed points, where you have here 4 inequivalent fixed points, and you have a set of discrete parameters. First of all, the brane here is not passing through the origin, so I have a displacement from the origin. That's one discrete parameter. And then I have a so-called Z2 eigenvalue, which you can view as in which way I'm going around the exceptional cycle at the fixed point. And then the last thing I have is that since I'm passing through 2 different Z2 fixed points, I can go the same way or the opposite way around the 2 different fixed points. So if it's the opposite way around, I've switched on a discrete Wilson line. So I have these 3 different sets of discrete parameters, and I have again a relation of the torsion, then the exotic orientifold plane, and once I've chosen the exotic orientifold plane, I have a prescription on what happens with my twisted sectors. So this eta I is again a sign factor which comes from the exotic orientifold planes. Now, the branes where you get a gauge enhancement have to be topologically invariant under the orientifold projection. That can only happen if the branes are parallel to some orientifold plane, and we have these 4 different types of orientifold planes. And then you have to look at the twisted sectors. They have to be invariant as well, and that's why we need this factors eta. And as you can see here, there's some minus sign from the construction, and you get some sign factors which have B as the shape of the torus, if it's like a rectangular torus like here, or if it's a tilted torus entering in here, and then the discrete factors, the displacement, and the Wilson lines. This classification is independent of the Z2 eigenvalue. That goes for any Z2 eigenvalue. The old known result is basically for this shape of the torus, the untilted case, where here always the exponent is 0. In that case, you obtain invariant planes always if they are parallel to the one exotic orientifold plane, and then it's for any choice of the other discrete parameters, you will always get symplectic gauge groups. So that's an old result by Blumhagen, Swittich, Marsh, Cesano, and Shu, basically, which was used for model building and for K-theory constraints, where we need probe branes that have sp2 gauge factors. On the other hand, I have an example where I have only tilted tori, so not rectangular, but I have a 60-degree torus. And then we have these non-trivial factors here, and then you get a relation either parallel to the exotic orientifold plane, the usual SP factor if these parameters are 0, or suddenly an SO type gauge factor if the parameters are 1 instead. And so it's less because here it's not an arbitrary choice of the parameters. There's not a mixed case like here in the untilted case, but I get again different orientifold planes, so in total, different invariant branes, so the total number of invariant branes stays the same if I have a tilted torus, but it's here then vice versa an SO or an SP gauge group. And that's of course a drastic change if I want to do model building, because if I want to realize the weak interactions by an SP group, I have just half the amount of SP groups. And also if I'm talking about consistency conditions, we have this K-theory constraint where we use probe branes of sp2 type. Again, here it's only half the amount of equations that I need to use. If you talk about factorized 2 tori, there are just 4 different ways of having discrete torsion with a Z2 times Z2m. So the Z2 times Z2 case is the one here I've always listed without torsion and with torsion, so that you can directly compare the number of moduli. So for Z2 times Z2, you exchange only Kähler and complex structure moduli, but you don't reduce the number of moduli. So that's the case that was looked at by Blumhagen and others, and some local models were built, but to my knowledge, not a single model which is globally consistent and contains the standard model was found. The Z2 times Z4 would be the next simplest, but the fact that here we don't get more 3 cycles means that we can't use it for model building. So there are 2 cases left over, Z2 times Z6 and Z2 times Z6 prime. In both cases, you can see that from the case without torsion to the case with torsion, the total number of moduli you have reduces. You don't get rid of all the moduli, but you reduce the number. And I will show you one example here in this case, because it's somehow the cleanest case to start with, because here you don't get mixings between different factors. It's just Z2 sectors contributing and not others. So the geometry of this last case is that we have 3 2 tori, which are each of SU3 type. So you have a 60-degree angle here. You have these 2 generators of the Z2 and the Z6 prime, which I've denoted in pink and in bright blue. And then since we have an orientifold, we have 2 orientations of each 2 torus lattice, which respects the orientifold. It's either the orientifold plane is lying along the horizontal direction, or it's lying along the diagonal direction. So a cycle is then of the form, a rigid cycle is of the form that it's 1/4 times the bulk part plus contributions from the fixed points. You can explicitly spell out the contribution from the bulk part in terms of 2 cycles that are the basic cycles of the torus. In this case, due to these 6 images, there are only 2 independent ones where you have some numbers that are the so-called bulk wrapping numbers. For the exceptional cycles, you have a similar picture. You have Z2 twisted cycles, and you have prefactors, which are again related to these 1 cycle wrapping numbers. So you can use these and first of all look at the tadpole cancellation conditions. So D-Brane charges have to cancel against orientifold plane charges, and you can go through the list of different lattice orientations. It's only 4 because you only have to distinguish how many A-type or B-type orientations you have. So 3 A-type, 3 B-type, and the other cases. So if you write down the list, you can notice some symmetry that the A-type and the B-type have the same maximal rank, and there's a symmetry where if you exchange these bulk wrapping numbers x and y in this way, while also exchanging the role of the different orientifold planes, you will see that you get the same ranks out and the same models. Okay, so well, you have this maximum rank then for the A-type torus, which is 16 in one case of the choice of the exotic orientifold plane or 8 else, whereas here it's 8, or you even have a model where you have an orientifold of type 2A string theory which doesn't have any D-Branes. So when you start model building, I will skip the upper part. We want to impose that we really don't want to have any moduli, so no adjoints, and we realize that is only possible on the very shortest cycle and only for some very special choices of the discrete parameters. If you furthermore don't want to have symmetric or antisymmetric matter of the strong interactions, we are even forced to a specific choice of the exotic orientifold plane, and if that was just for the QCD stack, 3 generations even forces us for the second stack to have the same bulk part cycle, and so it's really very, very constraining, and for the other type of lattice it doesn't work at all without any matter, exotic matter. So just to give you one example of a spectrum, you have here 3 generations of left-handed quarks and leptons together, 3 generations of right-handed quarks and leptons, and you have here 1 Higgs generation. And if you see here, it's really only SU4, SU2, SU2 because all the U1 factors are anomalous, but since the anomalous still give us selection rules on which kind of couplings are allowed, only the first left-handed, first right-handed, and the Higgs lead us to a Yukawa interaction. So at leading order in perturbation theory, there's only 1 massive generation, like in the talks by Angel Uranga, for example. You see there's still some bunch of non-chiral stuff we have at the moment, but you see that there's a drastic reduction in terms of what is on the QCD stack. That's the only thing that has a QCD charge, and here's my conclusions. So you have these branes with discrete torsion where you have some choices of backgrounds where you can do model building. You drastically reduce the number of both closed and open string moduli. Something I didn't have time to talk about is because the orbifold symmetry is bigger than in Angel Uranga's talk. The selection rules on Yukawa couplings are even much stricter than before. So I showed you an example, and as you can guess, we are still working on it. But one nice thing is also we have gauge coupling unification in these models because we have these strong restrictions on model building. So thanks a lot.
So do you want to start getting your talk ready, and are there any questions? So can you get the standard model?
So far not yet. We are still working on it, but Pati-Salam is always much, much easier to get then. So it seems left-right symmetric is much easier. It's very hard to get separately 3 right-handed generations of up-type and down-type quarks without introducing other exotic stuff.
So can I, so with the couplings, you say there is more than strain?
Yeah, the reason is that if you have the torus, you have just 1 brane. If you have, for example, a Z3 symmetry, you have the brane and you have images under the brane. And then you have the different quark generations can be localized on different images under this Z3 symmetry. And then it can happen that you have, for example, for the first quark generation, the triangle closes, but the second quark generation sits on a different Z3 image. But only the first left-handed quark and the right-handed and the Higgs don't change the position, and then you don't have a closed triangle anymore. So it's basically more restrictive. It doesn't open up new avenues.
Let's thank you.
Yeah.